welcome to the fascinating world of analytical chemistry. Have you ever wondered how scientists figure out exactly what's in a sample of water, air, or even food? Analytical chemistry does just that. It involves studying substances to both identify and measure their components, both qualitatively and quantitatively. This helps us understand everything from pollution levels in our environment to the purity of the medicines we take. Analytical chemistry isn't just for labs, it's at the heart of countless industries like pharmaceuticals, environmental monitoring, and forensics. Now, let's break this down into two main approaches: qualitative and quantitative analysis. While quantitative analysis measures the exact amount of a substance, qualitative analysis focuses on figuring out what substances are present. So, in a way, qualitative analysis is like detective work, identifying the culprits in a chemical mix. Imagine you're in a chemistry lab trying to figure out what's in an unknown solution. This is where qualitative analysis comes in. It's all about identifying the substances present without measuring how much of them there are. Think of it like a puzzle where you use clues to piece together the identity of the unknown. One of the most common methods for this is through chemical tests. For example, when we add sodium hydroxide to a solution, we can see the formation of a precipitate. The color and solubility of this precipitate give us clues about the metal ions in the solution. Some metal ions, like iron, form reddish-brown precipitates when reacted with sodium hydroxide, while others, like copper, form a blue precipitate. These reactions are key to qualitative analysis because the chemical changes that happen, like color shifts or the formation of a solid, help us deduce what's in the sample. Let's zoom in on sodium hydroxide, a powerful tool in qualitative analysis. Sodium hydroxide, or NaOH, is a strong base that dissociates completely in water to give hydroxide ions. This makes it an excellent reagent for reacting with metal salts. When sodium hydroxide is added to a solution containing metal ions, it can form insoluble metal hydroxides, which are often the key to identifying those metals. For example, when sodium hydroxide reacts with copper sulfate, it forms a light blue precipitate of copper, hydroxide. The fascinating thing here is that sodium hydroxide helps us see these metals through the changes in color and solubility. Think about it. Just by looking at the precipitate, we can tell which metal is in the solution. These tests are fundamental in both educational and professional laboratories. Now, let's move on to ammonium hydroxide, also known as ammonia solution. Unlike sodium hydroxide, ammonium hydroxide is a weak base, which means it only partially dissociates in water to produce hydroxide ions. However, this doesn't stop it from being a valuable tool in qualitative analysis. One of the unique things about ammonium hydroxide is that it can help us differentiate between different types of metal ions. For example, when ammonium hydroxide is added to a solution containing iron, ions, it forms a characteristic brown precipitate of iron, hydroxide. This is a clue to the presence of iron in the solution. Ammonium hydroxide is also important because it doesn't form precipitates with all metal ions, which makes it useful for narrowing down what we are dealing with in the solution. So, how do we use sodium and ammonium hydroxide to identify metals? Well, it all comes down to how different metal ions react with these hydroxides. Some metals, like copper and iron, react to form insoluble hydroxides, which appear as colorful precipitates. Copper sulfate, for instance, reacts with sodium hydroxide to form a blue precipitate, while iron, chloride reacts to form a reddish-brown precipitate with ammonium hydroxide. These reactions are really useful because each metal has a distinctive reaction pattern, and by observing the precipitate's color, we can narrow down which metal is in the solution. These tests are like little chemical fingerprints for metals, and they play a huge role in labs that analyze substances for purity, contaminants, or composition. Analytical chemistry isn't just confined to the laboratory, its applications are everywhere in the real world. Think about how crucial it is to test the water we drink, the air we breathe, and the food we eat. Analytical techniques help ensure that these substances are free from harmful contaminants and are safe for consumption. For example, in the pharmaceutical industry, analytical chemistry is used to check the purity of drugs, ensuring that the right amount of active ingredient is present and there are no dangerous impurities. It's also essential in environmental monitoring, where scientists use chemical analysis to detect pollutants in rivers or air. In forensics, analytical chemistry helps determine the presence of drugs or poisons at a crime scene. So, the next time you see a bottle of clean water or take medicine, know that analytical chemistry made sure it was safe for you. To sum up, analytical chemistry is like a powerful microscope, helping us identify and measure substances in everything from our environment to our food and medicines. Through qualitative analysis, using reagents like sodium and ammonium hydroxide, we can identify the metal ions in a sample by observing the colors and solubility of the precipitates they form. From identifying metals to ensuring product safety, analytical chemistry is vital in countless fields. I hope this session has shown you that chemistry isn't just about equations, it's about understanding the world around us. Thanks for watching, and I'll catch you in the next topic where we'll dive deeper into chemical reactions and their applications.